So here is the topic of our video, and our objective is this. And when I say represent, I mean you're going to draw some stuff about it. And uh, this is for just a single step reaction. So if I knew something about a reaction, in this case I know that water is exothermic, the way I would represent that in this scenario with these reaction profiles is with these little curves. And you're going to need to know how to draw them and what they mean and how they're drawn and what different values you can glean from them by understanding how they're set up. All right, so this is what an exothermic one looks like. All of these reaction profiles have the same axes. The reaction coordinate is the term that the AP curriculum uses just to describe what the things are going through as they progress. It goes from the reactants to the products, and then it goes up, gains energy, and then goes down, and has more energy than it started with. All right. Now, this distance represents the activation energy, the minimal amount of energy that it needs to occur. This distance is the change in enthalpy. And the reason this is endothermic, is it's got a positive enthalpy value in that heat is absorbed from the surroundings into the system, into the reactants, to allow them to turn into the products. Now, the exothermic is going to look very similar to the endothermic in the sense that it's going to have that bump thing, the activation energy, but this time the reactants are going to have more potential energy than the products. So there's a net release of energy. This distance here from the reactants to the top of this bump, the speed bump, or the hill, is still the activation energy. This distance is the enthalpy value. However, in this case, it's going to be negative in that the energy will be released from the reactants into the surroundings, not absorbed. All right. Now, I just want to give you like a little visual of what these things look like. So this is our reaction: two diatomic molecules making two molecules. And this, let's just pretend this is exothermic. The reactants are going to look like this. The products look like that. At the peak here, the AP wants you to know this is the transition state. And that's when the molecules are kind of like oriented correctly and they're transitioning or have the potential to transition from one to the other. Um, and this state, or this transition state, is the same whether if I'm going forwards or backwards. All right. Now, I want to talk about what a catalyst does to these reaction profiles. If I had an exothermic reaction, what would a catalyst do? This is the catalyst. That's the that's adding a catalyst. The same thing is true for an endothermic, where this is the catalyst. This is my reaction without it, and this is the dotted is with. All right. So what is the catalyst doing? It's lowering my activation energy and therefore making it easier because the molecules or atoms or whatever need less energy to react. It doesn't affect any of the enthalpy values. It doesn't affect how much energy things have before or after. All it does is lower the activation energy. All right, let's go over some problems. Here we've got a reaction profile, and is it exo or endothermic? Well, you'd look at this value here, you compare the reactants to the products. It's definitely exothermic because the reactants are giving off energy to the surroundings. It's delta H, it's enthalpy change. It would be negative, all right, because it's an exothermic reaction. What's its rate? What's the order? Based upon this, you cannot tell, all right? You're not going to be able to tell this. You'd have to look at experimental data. All right, what about this one? Is it exo or endo? Well, it's clear that the products have more energy than the reactant, so this is definitely endo. What's the delta H? Well, you can actually calculate this. It's 9 minus 2, so it's 7 kilojoules per mole. What's my activation energy? That's the difference between 2 and 14, so it's 12 kilojoules per mole. And where's the transition state, or what's the transition state? The transition state is going to be right up here at the top of the peak, at the top of the hill. Okay, right there. All right, here we go. This is the combustion of octane, is it exo or endothermic? Here's that energy thing right there. All right. Therefore, energy is released. This is an exothermic reaction. What's its reaction profile? Well, it's going to have that classic step up, and then the reaction is going to go down. You wouldn't necessarily know based upon this how big to make the bump. All right. But you just want to make sure you make the bump. You don't want to draw it like this. Oh, I didn't do that right. All right. Not like that. That's not right. All right. Here we've got two reactions. Are the exo or endo? Well, these are both exothermic because in both cases the products have less reactants. Sorry, less energy than the reactants. What's going to be faster? You could argue that A would be faster simply because its activation energy is much, much lower. All right. Here are my sources, and these two were where I got some of these images. Thank you so much, and I hope you had a good day. Bye.